In the second part of the Week 5 lecture materials, we're going to take a look at more examples of regular expressions and also at some string handling functions that interact with or use regular expressions. I've started a fresh RStudio session and loaded and rerun my poem script. So we do have our poem available for testing. All right, and so we looked at these basic regular expression characters in part 1, and also at some of these extended regular expression characters in some later examples. Now, one of the important extended regular expression characters that we introduced are the parentheses that allow you to create a group. That's important not only for using \n to match the group later, but it also allows you to do things like collecting together a sequence of characters for use with other regular expression characters like the vertical bar meaning or, as well as the star meaning 0 or more of, the plus meaning 1 or more of, and the question mark meaning 0 or 1 of. So I want to show some examples of those kinds of things. Also, I'm going to go ahead and introduce 3 more of the, well, it's sort of 3 variations on one more regular expression, using the curly braces. So some regular expression followed by some number in curly braces means to match a sequence of exactly n of that regular expression. An n followed by a comma means to match n or more of that regular expression. And 2 integers separated by a comma, m and n here, mean to match between m and n sequential occurrences of that regular expression. All right, so let's take a look at examples of these things. Here's our poem, and here's our little program that loads in the poem. And we used strdetect to identify which strings, which lines within the poem matched our regular expression pattern. And the filter function produced for us a tibble of the portion of the poem data frame that matches that regular expression. Okay, and we saw our initial example was, our pattern was capital H, meaning we're looking for capital H at the beginning of the line, and whoops, and filter poem df strdetect poem with that pattern. Piam. Oh, goodness. Poem DF, not Piam DF. There we go. All right, all right. Now, one of the misconceptions that people sometimes have about square brackets is that you can somehow use square brackets to match a sequence. But square brackets always matches one single character from among the set of characters that you give in the square brackets. So if you use this pattern, and this is fine, we'll go ahead and type this in. Pattern is square bracket AAAAA. That does not mean that we're looking for a sequence of 5 A's. What it means is that we're looking for an A, or an A, or an A, or an A, or an A. And in fact, it's no different from just looking for plain old A. What we're saying is we want to look for any one of the characters in this set but the only character in that set is little a. So there's really no point in using the square brackets at all here. It'll work fine, and what I get is all of the lines from the poem that somewhere contain a little a. Whoops, I'm having trouble highlighting here. So there's a little a, here's a little a, here's a little a. We're not looking for a sequence of 5 a's. Likewise, if I were looking for ABBA in square brackets, that is not the famous old Swedish disco group. That just means we're looking for a little a or a little b or a little b or a little a. And it's the same thing as just looking for a little a or a little b. I've just typed some extra unnecessary characters. If I put most regular expression characters inside square brackets, that turns off their special meaning. So as an alternative to looking for a literal dot character by putting a pair of backslashes in front of it, you might find it more convenient to just put square brackets around it. Because the square brackets mean I'm looking for a character which is one of dot. And here the dot just means dot. It doesn't mean any individual character. So if I use that as my pattern, okay, square bracket, dot, close square bracket. If I use that as my pattern and do a filter, I get the 2 lines that I modified to end with dot rather than with exclamation mark. Most of the regular expression special characters can have their special meanings turned off by including them between square brackets. So this is just a rather longer example. I'm looking for either a dot or a star, asterisk, whichever. That character actually has a whole bunch of names as well. Some people call it the star, the asterisk, the splat, and so on. So I'm looking for either a dot or a star or a plus symbol or a literal open parenthesis character or a literal close parenthesis character or a literal $sign. All of these characters are just treated as ordinary characters because I have enclosed them within square brackets. Now, I could, to be masochistic, use ORs. These are regular expression OR characters with parentheses around the whole mess and double backslashes in front of each of the individual regular expression characters. So what I did in square brackets here is equivalent to saying I'm interested in looking for a literal dot or a literal asterisk or a literal plus or a literal open paren or a literal close paren or a literal $. Symbol. Obviously in that case the square brackets is a whole heck of a lot less typing. Now, another example that I have frequently seen people do by accident, especially if they're dealing with numbers, is to try to use a set of square brackets to describe a range of numerical values. This is the kind of thing that you might see if someone's looking for a value ranging between might as well call these dollars, $1.00 through $9.99. Okay, so the desire here is to look for patterns of characters consisting of a digit followed by a dot followed by 2 digits. And so the first digit could be anything between 1 and 9, and so on. But unfortunately, when you use, well, I said unfortunately, I don't know if it's unfortunate, but it is just a fact that if you use one pair of square brackets, that means you're looking for one character. And that one character may be any one character within the set or range of characters that you've specified. So in regular expression terms, we're not looking for 1.00 through 9.99. What we're looking for is either a 1 or a dot or a 0 or any of the characters between 0 and 9 or a dot or a 9 or a 9. So in other words, the upshot is that this elaborate but inappropriate pattern is equivalent to just saying that I'm looking for either a digit, that is some character between 0 and 9, or a dot. Okay, so don't get yourself confused into thinking you can use square brackets to look for ranges of numerical values. Now, there are some characters that are used within square brackets for special purposes. For example, if we have an opening square bracket, obviously we have to have a closing square bracket to match. But it turns out that the closing square bracket only means that behavior, only means to close the open square bracket if it is someplace other than the first character in the pattern. So you can, through trickery, indicate that a closed square bracket is one of the characters you're interested in matching by putting that closed square bracket as the very first character after the open square bracket. Now, another special character inside of square brackets is the caret symbol, and we have used that to match some character that is not within the set. But the caret symbol only has that special meaning if it's the very first character in the pattern. If the caret symbol appears anywhere else in the pattern, then it's just treated as an ordinary character. Similarly, the dash, which we use in ranges like 0-9, won't have that special meaning if it's the very last character inside the square brackets, or for that matter, if it's the very first character inside the square brackets. So by positioning the closing square bracket first, the caret not first, and the dash last, I can actually use square brackets to look for either a closed square bracket or a caret or a dash. It's equivalent to using parentheses around an or, looking for a literal closed square bracket or a literal caret symbol or a dash. Here I don't have to bother putting double backslashes in front of the dash because the dash only has a special meaning if it's within square brackets and between two characters. Okay. Now, a regular expression character that I felt like I didn't really do a good enough job on is the question mark. The question mark means that something is optional. In this instance, right before the question mark, we have a little s, indicating that that little s is optional. It may or may not exist. What this pattern is looking for is either Mr. dot space Jones or Mrs. dot space Jones. And the only difference between Mr. Jones and Mrs. Jones is that S. So by indicating that the S is optional, that is, it might or might not be there, we can match both Mr. followed by dot or Mrs. followed by dot followed by space Jones. Okay, so the question mark is very useful for indicating whether something may or may not exist. As another example, an integer may or may not have a unary plus or minus in front of it. So an integer could consist of a plus or minus. And notice that because we put the minus last, that the minus is just a minus sign there. It's not treated as specifying a range of characters. And that's optional. And then following that, we have one or more digits. Okay, and I guess we should really have our caret in front and our dollar in back if we want to check whether a certain string matches an integer with an optional plus or minus sign in front of it. Okay, so that's what the question mark is about. Now, the star, as we've seen, modifies the meaning of the character ahead of it. I should say modifies the meaning of the regular expression ahead of it. But if I type it just following an ordinary character, if I say th star, then the star only applies to the h, and the meaning of this pattern, th star, is to match a t followed by 0 h's, or to match a t followed by 1 h, or a t followed by 2 h's, or 3 h's, or 4, or 17, or 99, or a million, or whatever. So this pattern requires there to be a little t, and then there may be some arbitrary number of little h's following that little t. One of the important uses of the parentheses is that, well, come here now. I'm going to highlight that parenthesis. I said, there we go, there we go, there we go. One of the important uses of the parentheses is that you can use it to create a sequence or a group of characters to which you can apply the star to mean you're interested in looking for sequences of 0 or more of that sequence. All right, so 0 or more of th can match nothing, and I've indicated nothing by just an empty string here. Or it can match the sequence of characters th. That's one occurrence of th. Or it can match th, okay, 2 occurrences of th. Or th. So any sequence of the 2 characters th is what's matched by the th in parentheses followed by the star. If instead of the star we use the plus, then the plus requires there to be at least one occurrence of th. So the empty string would not be a match. And there may be more occurrences of little th following that. What if we wanted to test, whether a string contained exactly 2 little t's? Well, let's do that. So let's set our pattern to match exactly 2 little t's. What that means is that between the beginning and the end, we're only allowed to have 2 little t's. But the question is, what are we allowed to have before the first little t? What are we allowed to have between the 2 little t's? And what are we allowed to have after the second little t? Well, before the first little t, we're only allowed to have things that are not little t. And there may be any number of those things that are not little t's. Then, between the 2 little t's, we also may have any number of things that are not little t's. And between the second little t and the end of the line, we may also have any sequence of things that are not little t's. Okay, so I believe we'll find in our poem, okay, we've got exactly 2 lines in our poem that contain 2 little t's. In the first case, it's just the 2 little t's in little. All right, there are no t's in front of that first little t. There are no t's between the two t's. And there are no t's after the second t. In the second example, we've got our first t in the word with and our second t in the word gently, and those are the only two little t's that exist within that line of our poem. Right? If we wanted to look for lines that contained exactly 3 e's, let's say. So let's change, instead of t, we're going to use e. So we want not e's followed by an e, then not e's followed by an e, then not e's followed by an e, and then more not e's up to the end of the line. So this is looking for exactly three little e's. And I actually don't know if we're going to get any matches. Yes, we got a couple. So the little crocodile has 3 little e's in it, both for the title and for the first line of the poem. Okay, now it gets pretty tedious typing this square bracket, caret, e, close bracket, star over and over and over again. So the curly brace notation for being able to count a specific number of occurrences is useful. If I say little t and then curly brace 4, what that means is I'm interested in matching 4 little t's in a row. Okay, so t curly brace 4 close curly is the same as just typing t, 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 t. If I say 2 comma 4 in curly braces, that means to match either 2 t's or 3 t's or 4 t's. And so it's as though I had typed this parenthesized sequence of possibilities. 2 little t's or 3 little t's or 4 little t's. Now, to make use of this with looking for an exact number of some character or some character sequence in a string, notice here that I've put my, here I'm looking for exactly 4 t's. I've put my square bracket, caret, t, close bracket, star. That means non-t's, 0 or more things that aren't t's followed by a t. Now, I can have exactly 4 sequences of non-t's followed by a t, and after exactly 4 of those sequences, I'm only allowed to have non-t's left. So let's give that one a try. All right, let me get back my, whoops. Well, let's look for 4 e's instead, since I've got that example conveniently here. So I'm going to create a group consisting of not e's followed by an e, and we're going to have 4 of those. Then we're also going to have a bunch of possible not e's all the way to the end of the line. Okay, and we do have 3 lines that have exactly 4 e's. So here we've got 1 e, 2 e's, 3 e's, 4 e's. When people are looking for exactly a certain number of characters or exactly a certain number of patterns within a string, the most common mistake is to forget the caret or the dollar. So let's get rid of the dollar and the caret. This means that we're looking for lines that contain 0 or more e's followed by an e, 4 of those, followed by 0 or more things that aren't e's. This, it turns out, means to look for lines that have at least 4 e's. But there may be more than 4 e's. I'm not sure we have any such lines. We do. Here we have 1, 2, 3, 4 e's. All right, and we said we wanted to match 4 e's, optionally preceded by things that aren't e. But we haven't indicated that we only want 4 e's. So we're actually getting a match on a line that contains, well, specifically we're getting a line that contains at least 4 e's. But in this case, there are more than 4 e's in that particular line. All right. Well, okay, so as I said at the outset when I started talking about this, regular expressions are one of my very favorite tools for wrestling data into an appropriate format where it can be fed into, R or Python or some machine learning algorithm or whatever it may be. And so it's good to have a very thorough and clear understanding of these things. Let's take a look at functions now that make use of regular expressions. We've already been using stir-detect in my as my selection criterion for filtering to select just certain lines from my poem data frame. Now, in this case, each line of our poem is actually a one-item character vector. You can use stir-detect on multi-item character vectors as well. Let's say, in fact, let me copy and paste this so I don't have to retype it, that instead of a single string, I have a vector of strings, or a vector of character objects in R speak. Now, if I say stir detect in my character vector, my regular expression here is just going to be the ordinary character D. Well, I've got 3 character objects, string objects, in this vector, and what I get back, therefore, is a vector of 3 logicals. There is a little d in the first character object, the first string, right at the end. There is no little d in the second string, and there is a little d in the third string. So I get true, false, true. grep is rather like stir-detect, but instead of giving back a vector of booleans, a vector of logical values, what it gives back, an integer vector of the items that do contain matches. So I've still got my same CVEC here, and I'm saying grep for the pattern D in CVEC. You'll notice that the options here for the grep function are in the reverse order for the stir-detect function. This is basically how the command is used in a Unix system. So if you have your $ prompt, you would say grep for D in some file. And the grep command would search all of the lines in the file in file.txt, and any line that contained a little d would be displayed. Okay. But the grep function just tells me that the first string in my vector of 3 strings, as well as the third string in my vector of 3 strings, do contain that regular expression pattern, which is just the regular character D. All right? So, by the way, people sometimes wonder what grep means. Grep is actually the acronym for a command in a very old Unix editor called ed, which is a line editor. Way back when Unix originated, people were still using paper teletypes as terminals for the most part. And so the whole concept of a screen-oriented editor just wasn't, in the realm of the possible. And in the ed editor, if you wanted to see all of the lines in the file that you were currently typing that contained some regular expression, you would type this editing command, g/regular expression/p. And that would scan through your file and print out each line if it contained that particular regular expression. That facility of the editor was so useful that they literally copied out that part of the code from the editor and patched it up and created the grep command. Okay. If I search for a regular expression that just doesn't exist in the character vector, then I get back an empty vector of integers. Okay, so integer 0 is how R tells me that I have an empty integer vector. As an alternative to getting back the indexes in the vector of the strings that do contain my pattern, I can add the argument value equals true. Well, the argument, the value with a value of true. And that will cause values rather than indices to be displayed. So if I do a grep for D in CVEC with value equals true, then I get back that hi world contains little d and today contains little d. Similarly, if I searched for a regular expression that doesn't exist with value equals true, instead of getting an empty integer vector back, I get an empty character vector back instead. The sub function does a substitution in a vector, and by default, the substitution will replace the first occurrence of some regular expression with some replacement string. And let's, all right, we've still got our same CVEC here, C vector, character vector. If I say substitute in place of A through E, okay, so my regular expression is my first argument. So substitute in place of, this is a lowercase letter, A, B, C, D, or E. So substitute in place of the first A, B, C, D, or E that's found in each string, the character X. And CVEC is the vector of character objects, the vector of strings that we're going to process. And as output, I have the same character strings that I had for input, but the first occurrence of some letter, A, B, C, D, or E, in each string gets replaced with X. In the first string in the vector, the only one of those possible characters, A through E, was the very last character, so that got replaced with X. In the second string, our first one was the little a in the word R. And in the third one, it was the little d in today. But notice that those second and third strings do contain other characters in the range from A through E. There's an E here, there's an A here, but those didn't get changed. Only the first occurrence of a letter between A and E got changed. If you want to do a global substitution, that is, you want to change every occurrence in every string, then you use the gsub function rather than the sub function. All right, so let me just get back my sub function call and put a G in front. And notice now that in the first string, which started out as hi world, the only character in there between A and E is the D at the end, and that got changed to X. In the second one, how are you, we have an A, which is in the range from A to E, as well as an E, which is in that range, and so I get how X are X, you. And then in the final string today, I've got the D and the A, both of which get changed to X. Okay, so we have a tool that allows us to change the first occurrence of a regular expression to some string. We also have a tool that allows us to change every occurrence of some regular expression to a string. But how would I change the second occurrence of some regular expression to some string and leave the first one and all the trailing ones unaffected? Well, the trick here is to change the first occurrence to some string that's easy for you to remember and that you're quite certain does not exist elsewhere within the line. All right, so QWERTY in all caps is a pretty good choice often. And then you do another substitution of the first occurrence and then substitute QWERTY back to the original character. So let's step through what's happening here. So I'm changing CVEC here to just be one string with more text in it. All right, this is a test. And what I'm wanting to do here is to change little s to x, but only the second occurrence. In the string, there are 1, 2, 3 s's, and I want to change the second s, not the first one or the last one. So I do my first substitute in place of s, QWERTY in all caps from CVEC, and I need to save that into an intermediate variable. All right, so the first s has now been changed to QWERTY in all caps. Therefore, if I do the same thing again, but this time change the s to an x, this substitution is going to change the first little s to an x with CV1 as input. So that means that this little s is going to get changed to x. All right, so that got changed. And now I just want to undo the QWERTY here. So I'm going to say CV3 gets substitute in place of QWERTY the string s. And so CV3 now is the goal that I originally wanted. I wanted to change the second s in this string to an x. And I was able to accomplish that through a little bit of trickery. All right, now grep, sub, and gsub are base R functions. They're standard old-fashioned R functions that have existed way since the original S language. And they're basically features directly stolen from Unix commands and Unix editors. In the tidyverse, the alternative to sub is called stir replace. And casually, it looks very much like sub, and so you might wonder, well, who cares? But the difference is that stir replace works with pipes, whereas sub and gsub do not. And stir replace works with pipes through the simple mechanism of having the string that you're modifying be the first argument rather than being the last argument. All right, so let's see what's happening here. Now, rather than using these three intermediate variables, I could have nested these sub calls inside of each other. I could have said CV3 gets sub of sub of sub of change S to QWERTY in CVEC, and then change S to X in the result of that first substitution, and then change QWERTY to S in the result of that second substitution. All right, so I can nest these function calls. Let me call this variable CV3A. I can nest the function calls, and now CV3 and CV3A have the same values. But nesting function calls is a giant pain, whereas pipes are really easy to use. All right, so CVEC this is a test, and I'm going to say into CV3, let's call this one CV3P for pipe. Let's stir replace in CVEC, or reading from CVEC, little s, and replace that with QWERTY. All right, so that's step one. Now I can just take this and pipe it into another stir replace. And this time, since I'm getting data from a pipe, I don't need to give CVEC again. And I'm going to say replace S with X and pipe that into stir replace and replace QWERTY with S. Poof, and now I have accomplished changing the second S to an X and leaving the first S as an S. So CV3 was using the sub function, and CV3P is using stir replace with a pipe, and I get the same result. And after you use using pipes, if you're not already, you'll realize that that's a much simpler way to go. And you don't end up with these intermediate variables sitting around that you don't have any need for. Okay, stir split will split a string according to some regular expression pattern, and it will work on n item character vectors. So here we've got this version of CVEC is back to the one that has 3 string objects in it, 3 character objects in it. Let me go back and find that so I don't have to retype the whole thing. All right, it's got to be here somewhere. There we go. Okay, so now I've got CVEC back to being a vector of 3 character objects. Hi world, how are you, and today. If I say stir split CVEC, notice that the argument for the string vector goes first so that it can be used as part of a pipeline. And I'm using a regular expression here, the square brackets. Well, even if I just said A, even if I just say A, that is a regular expression. That is a regular expression that matches little a. Here I'm using a regular expression special character, namely the square brackets. And I'm saying, all right, I want to split this. I want to split the 3 string items in the CVEC vector at either little a's or little o's. So, in the first string, if we look at that, there are no little a's. There is one little o. So that string got split just once, and we end up with hi, comma, w, and urled. The second string, how are you? Well, that has 2 O's and an A. So that thing ends up getting split into 4 pieces. H, W space, RE space Y, and U. And then the final string, today, has 1 little O and 1 little A in it, so it gets split into 3 pieces. Little t, little d, and y question mark. So what I get out of this is a list of character vectors. And the number of items in each of those character vectors is going to depend on how many times the regular expression occurred in the original character object in that vector. Okay, stir locate tells me the start and the end of the first I didn't say first in my description. Naughty me. Okay, so it's going to return to me the start and the end indexes of the first occurrence of some regular expression in each of the character objects in this vector. Just to be a little fancier, here I have a regular expression in which the first character can be either a little w, a little r, or a d. The second character is anything except a space. All right, so square bracket, caret, space, close square bracket means any character that's not a space. So we're looking for w followed by something that's not a space, or r followed by something that's not a space, or d followed by something that's not a space. Right? So if we look at our first string, the first one of these WRD characters that I get to is this w, and fortunately that is followed by a character that is not a space. So WO is our first match. Then if we look at the second string, well, we do have a W here, but it's followed by a space, so that one is not going to work. Then we come to an R, which is followed by a character that's not a space. So there's our second match, or I should say our first match in our second string. And then finally, here is our first match in our third string. And what stir locate does is to return to me a matrix of the start and end indexes of these regular expression patterns in the first string, the second string, and the third string. Let's see if that makes sense. So H is character sub 1, 2, 3, 4. So W is character sub 5, and O is character sub 6. All right, so 5 and 6 are the correct indexes for the WO in High World. In the second one, 1, 2, 3, 4, 5, 6 is the first character, 7 is the second one. And in today, 1, 2, 3 is the first character, 4 is the second character. So those are correct values. Now, stir-locate has an all version that gives me back a list of matrices for all of the matches. And here's what that would look like. I guess I didn't run my test here. I should probably do that. All right, so CVEC is what we said, and stir-locate in CVEC of either a WRD, a W and R, or a D, followed by something that's not a space. And we get back the matrix that I claimed we would get. For stir-locate all, we get back a list of matrices. So let's see how that's going to be. Stir-locate all. All right, if we look through these strings, we're looking for either W, R, or D, followed by a character that's not a space. Here we have a W followed by an O. We also have an R followed by an L. We also have a D, but that D doesn't have anything after it. So we have two matches in High World. In the second string, well, we discovered we've got a W that's followed by a space, so that's not a match. We've got an R followed by an E. There are no more W's, R's, or D's in there. So we only have one match in the second string. Similarly, we only have one match in the third string. So my list of matrices is going to have two matches for the first string, High World, one match for How Are You, and one match for Today. Stir extract is a bit like stir locate, except instead of telling you where the matches are, stir extract shows you the matches. So if I say stir extract from CVEC, that same pattern, W or R or D, followed by something that's not a space. Instead of getting this matrix of where these matches are, I get a vector of the matches. Okay, so I get a vector showing me that WO is the first match in the first string, RE is the first match in the second string, and DA is the first match in the third string. There's an all version of stir extract, which you won't be shocked to learn shows you all of the matches. Turns out there are two different variants, if you will, of stir extract all. By default, you get back a list of all the matches for each of the strings. All right, so I get back a list of 3 items. The first item is a vector of 2 strings that match our regular expression pattern in High World. The second item in the list is just the one match, RE from How Are You. And then the third item in the list is the vector of one match, DA. The alternative to this is if we use the argument simplify equals true, and here I guess we can debate whether this is really simplifying, but if we say simplify equals true, then we get a matrix of matches rather than a list of vectors of matches. Okay, so it's the same information, but we have a 3-row and 2-column matrix now in which the non-existent matches for the second string and the third string just have empty strings in them to indicate that there was no match. All right, so that is that. We have investigated a bit more about regular expressions, and I've had a chance to warn you about some popular mistakes that I see made frequently with regular expression special characters. And we've taken a look at some of the base R functions for dealing with string matching with regular expressions, and then several of the tidyverse versions. And the tidyverse functions are more convenient because they're designed to interact with each other through pipes. Basically, the vector of string objects is the first argument in each one of these functions, which automatically enables them to work with pipes, whereas the base functions can't work with pipes. Okay, so that is that.